The focus today is on kinetic separations in which we exploit differences in the intra-crystalline diffusivities of gas molecules in order to reverse the hierarchy of selectivities dictated by mixture adsorption equilibrium. In particular, we highlight the importance of thermodynamic coupling effects in kinetic separations. And we use the examples of separations of nitrogen-methane mixtures using LTA4A zeolite, nitrogen-oxygen mixtures using LTA4A zeolite, and carbon molecular sieves, and kinetic separations of mixtures of carbon dioxide and ethane using DDR zeolite. The material I will present today is largely based on my publication in 2019. There are also two other videos that provide background information on diffusion in crystalline micro-porous materials and transient breakthrough simulations. These videos can be viewed on my YouTube channel. Many natural gas reserves contain nitrogen in concentrations ranging to about 20%. To meet pipeline specifications, the nitrogen level must be reduced to below 4%. Large majority of nitrogen removal facilities use cryogenic distillations, but such units are economical only for large capacity wells. For smaller reserves, pressure swing adsorption technology has economic benefits, especially because the feed mixtures are available at high pressures. It is desirable to use adsorbents and PSA technologies that are selective to nitrogen. However, for most known adsorbents, the adsorption selectivity for nitrogen-methane mixtures is in favor of methane due to its higher polarizability. One practical solution is to rely on diffusion selectivities by using micro-porous materials such as LTA4A zeolite. The suitability of LTA4A zeolite for kinetic separations of nitrogen-methane mixtures was first suggested by Harry Hapgood in 1958. And the objective of this presentation is to examine the potential of LTA4A zeolite for nitrogen removal from natural gas streams. Hapgood in 1958 published a set of experimental data on transient uptake of nitrogen and methane in LTA4A zeolite at a temperature of 194 Kelvin. The data is remarkable in that it shows that the nitrogen uptake shows an overshoot in the molar loading, and the value of the peak is about 2.2 moles per kilogram, significantly higher than the value at equilibrium, which is 1.2 moles per kilogram. The uptake of methane, on the other hand, is monotonic, and the component loadings approach its equilibrium value in a monotonic manner. The attainment of supra-equilibrium loadings of nitrogen and transient overshoots are signatures of kinetic separations. Before we delve into the details of the Maxwell-Stefan modeling of intra-crystalline diffusion, let us gain a qualitative understanding of the motion of molecules within the cage window structure of 4A. Towards this end, I will play video animations prepared from MD simulations. There are many things to look at in the animations. Firstly, note that the blue-colored guest molecules are nitrogen. The green-colored spheres are the sodium cations, and the cyan-colored spheres are the methane molecules. You will also note when you observe the simulations that the green-colored spheres, that is the cations, act like goalkeepers in a soccer match, trying to prevent the intercage hopping of guest molecules. Another thing to note when I play the simulations is that nitrogen jumps lengthwise across the windows from one cage to the adjacent cage, and that happens in this window region. So if you want to have a look at nitrogen hopping, look at this window. If you want to see the goalkeeper sodium cations in action, look at this window. And for the duration of this animation, the methane molecule is unable to cross the window because the animation is only run for a short period of time. Let us have a look. Here's the goalkeeper. Here's the nitrogen molecule attempting to cross the window, and it has just managed to cross it. Play it again. Based on the MD animations shown on the previous slide, we conclude that the gas molecules jump one at a time across the narrow 4 angstrom windows. So the intercage jumps of gas molecules are uncorrelated. For this situation, the Maxwell-Stefan diffusion equations can be applied in their simplified form, in which correlation effects are ignored. For background details on the Maxwell-Stefan diffusion model, consult my publication of 2014, and see also the video presentation, Diffusion in Ordered Crystalline Micro-porous Materials, on my YouTube channel. The Maxwell-Stefan diffusion equations recognize that the proper driving forces for intra-crystalline diffusion of gas molecules are the chemical potential gradients. R is the radius of the crystallites, rho is the mass density, Q1 and Q2 are the component molar loadings of components 1 and 2. R is the gas constant, T is the temperature, and N1 and N2 are the intra-crystalline diffusion fluxes. D1 and D2 are the intra-crystalline diffusivities of 1 and 2 that signify molecule wall interactions. The chemical potential of any component in the adsorbed phase can be related to the partial pressures in the bulk gas phase from this expression, and therefore the chemical potential gradients can be written in terms of the gradients of the molar loadings by defining a matrix gamma ij of thermodynamic correction factors. The expression for gamma ij is given here, in which Qi is the molar loading of component 1, P sub I is the partial pressure of component 1. For a binary mixture, gamma ij has 4 elements that can be written in matrix notation as shown here. Gamma 1, 1 and gamma 2, 2 are the diagonal elements, and gamma 1, 2 and gamma 2, 1 are the off-diagonal elements. These 4 elements serve to interrelate the chemical potential gradients to the gradients of the molar loadings. If we ignore the cross coefficients gamma 1, 2 and gamma 2, 1, the chemical potential gradient of species 1 is proportional to the gradient of the molar loading of component 1. However, due to the presence of these cross coefficients, the chemical potential gradient of any component is dictated not only by the gradient of the component loading of component 1, but also the gradient of the molar loading of component 2. Put another way, the presence of these off-diagonal elements leads to thermodynamic coupling, in which the driving force of component 1 is related to the molar gradients of both components 1 and component 2. Indeed, the objective of this presentation is to show the importance of thermodynamic coupling effects on the description of transient uptake within a single crystallite and transient breakthroughs in fixed bed adsorbers. For the determination of the mixture adsorption equilibrium between the bulk gas phase containing nitrogen and methane and the pores of LTA4A zeolite, we need the Unary isotherms. I show here the data on the Unary isotherms for nitrogen and methane as published by Wilkins and Hapgood for a variety of temperatures ranging from 194 Kelvin to 343 Kelvin. The data at 5 different temperatures can be fitted with the single site Langmuir isotherm with temperature dependent parameter B, where E is the energy parameter. The Langmuir isotherms are named after Irving Langmuir, who obtained the Nobel Prize in 1932. For a single site Langmuir model, the energy parameter E can be identified with the isosteric heat of adsorption. The Unary isotherms for nitrogen and methane at various temperatures fall on a single line when plotted against the surface potential, and the surface potential serves as a proxy for the spreading pressure pi, which is determined from the Unary isotherm data. For background on the spreading pressure concept, see my video presentation on my YouTube channel. For both nitrogen and methane, the saturation capacity is 3.6 moles per kilogram, and this is advantageous because the mixture adsorption equilibrium can be described precisely using the mixed gas Langmuir model, as we shall see in the next slide. It is important to note, if the saturation capacities of nitrogen and methane are not equal to each other, we need to use the ideal adsorbed solution theory for calculation of mixture adsorption equilibrium. Based on the single site Unary isotherm fits for nitrogen and methane LTA for a zeolite, we can apply the mixed gas Langmuir model to describe a mixture adsorption equilibrium. The component loadings for 1 and 2, nitrogen and methane, are described in the mixed gas Langmuir by this expression, where we define theta as the fractional occupancy of nitrogen, theta 1, and the fractional occupancy of methane is theta 2, where the fractional occupancies are the component loadings divided by the saturation capacity, which is 3.6 for both guest molecules. The matrix of thermodynamic correction factors can be determined analytically, and the expression for the 4 elements of gamma are shown here, where you note that the off-diagonal elements, gamma 1, 2 and gamma 2, 1, are proportional to the component occupancies. Here are the calculations of the 4 elements for 50-50 mixtures of nitrogen and methane at a temperature of 194 Kelvin. This is relevant for modeling of the transient uptake experiments of Hapgood, which were also conducted for 50-50 mixtures at 194 Kelvin. The 4 elements of gamma are shown here as a function of the total pressure in the bulk gas phase. The continuous solid lines are the diagonal elements. Red is gamma 1, 1, blue is gamma 2, 2, and the off-diagonal elements are shown by the dashed lines. Red, gamma 1, 2, blue, gamma 2, 1. In the Unary regime at low bulk gas pressures, the diagonal elements are both unity and the off-diagonal elements are vanishingly small, and at zero loading, the off-diagonal elements are 0. As the total pressure increases, we note that the off-diagonal elements increase in magnitude and reach almost the values of the diagonal elements. And a different way of plotting these results is to determine the coupling factors, gamma 12 divided by gamma 11 and gamma 21 divided by gamma 22. These are shown by the red and blue lines, and we note as the pressure increases from 0 to 100 kilopascals, the coupling effects or the coupling factors increase from 0 to values in excess of 0.8. In other words, if the bulk gas pressure is 100 Kelvin at a temperature of 100 kilopascals at a temperature of 194 Kelvin, the off-diagonal elements are only slightly lower than the diagonal elements. This implies that the coupling effects are of significant importance in mixture adsorption. Let's model the nitrogen-methane mixture uptake in LTA4A zeolite using the Maxwell-Stefan diffusion equations. The D12 term signifying correlations between 1 and 2 need not be accounted for because the gas molecules jump one at a time across the windows from one cage to the adjacent cage of LTA4A zeolite. We take the diffusivity values based on the data provided by Habgood, and let's first consider the transient uptake simulations in which the thermodynamic coupling effects are duly accounted for. The uptake of nitrogen is plotted is followed here as it develops inside the crystallite of 4A zeolite. This is the surface of the zeolite, which is in equilibrium with the bulk gas mixture. This is the center of the crystallite. The nitrogen shown by loadings in moles per kilogram shown by these red lines. Note that this is the loading at the surface, and the peak loading is significantly higher, and it diffuses much faster than methane. And at this time, the maximum loading has been achieved, and the loading inside the crystal of nitrogen decreases finally to reach the value at equilibrium. So it undergoes overshoots as observed in the experiments. Let's now perform the same set of simulations, but now ignoring thermodynamic coupling and assuming that the matrix of thermodynamic correction factors is the identity matrix. In other words, gamma ij is the Kronecker delta. These simulations are shown here. Again, this is the surface of the crystallite. This is the center. The red line is for nitrogen. The blue lines are for methane. Nitrogen penetrates faster into these central regions, but you will note that no overshoot has been experienced so far by nitrogen. Methane is tardier in its uptake and takes a significantly longer time to reach equilibrium. But determining the spatial average of the component loadings as presented in the foregoing slide, we can determine the spatially averaged component uptakes for components 1 and 2, nitrogen and methane. The experimental data of Hapgood, shown by the blue circles for nitrogen and blue triangles for methane, are compared with the spatially averaged component uptakes from the simulation data. The continuous solid lines are the simulation results in which the thermodynamic correction factors are duly accounted for. The dashed lines are the corresponding simulation results in which the thermodynamic correction factors are ignored, and the matrix of thermodynamic factors is taken to be the identity matrix. We note that there is good agreement between the experimental data of Hapgood and the simulations in which gamma ij is properly accounted for. On the other hand, if gamma ij is taken to be the Kronecker delta, in other words, the thermodynamic correction factor matrix is taken to be the identity matrix, no transient overshoot for nitrogen is anticipated, as shown by the dashed red lines here. And there is poor agreement, qualitative and quantitative, with the experimental data of Hapgood. We therefore conclude that the Hapgood experiments with transient overshoots can be described only by a model that takes due account of thermodynamic coupling effects. Indeed, the transient overshoot of the more mobile guest is a signature of kinetic separations. There is another way in which we can plot this data, and that is in composition space. We plot the nitrogen uptake versus the methane uptake. These are the component uptakes at time t0 at the start of the experiment. And this point here is t is infinity, is when equilibrium is reached. The red circles represent the Hapgood data plotted in composition space. The red line shows the trajectory from time t0 to time t is infinity, the trajectory that is followed by in the simulations in which thermodynamic coupling effects are duly accounted for. And this is in good agreement with the Hapgood experiments. On the other hand, if thermodynamic coupling effects are ignored, the equilibration trajectory follows a monotonic path to equilibrium in quantitative and qualitative disagreement with the Hapgood experiments. So a signature of kinetic separations is that in composition space, the equilibration trajectory follows a scenic route. Let us examine the concept of the kinetic selectivity for binary mixtures. The kinetic selectivity is defined as the ratio of the spatially averaged component loadings for 1 and 2 divided by the corresponding ratio of the partial pressures in the bulk gas phase surrounding the particle. For the Hapgood experiments, the transient uptake selectivity determined from this formula are plotted here, as a function of the Fourier number. For comparison, the green line shows the kinetic selectivity that is calculated using a formula that is often used in the published literature as being the ratio of the Langmuir constants for components 1 and 2 multiplied by the square root of the ratio of the diffusivities for components 1 and 2. As shown here, the experimental data for Hapgood lie about a factor 2 above the value calculated from this formula. The continuous red line are the calculations of the kinetic selectivity from the simulations presented in the foregoing slide, in which thermodynamic coupling effects are duly accounted for. The blue line is the kinetic selectivity calculated from the simulations in which thermodynamic coupling effects are ignored. Looking at this data, we note that the formula that is widely used in the published literature is a limiting case of a model in which thermodynamic coupling effects are ignored. Put another way, the commonly used formula is based on a model that is not in quantitative agreement with the Hapgood experiments. Also shown on this graph by the dashed line is the adsorption selectivity, that is the ratio of the Langmuir constants. What we conclude from this comparison is that the simplified formula that is often used in practice must be viewed as being an approximate measure of the kinetic selectivity, whereas by taking due account of thermodynamic corrections, we may obtain selectivities exceeding that determined from the simple formula. Having established the importance of including thermodynamic coupling effects in the description of transient uptakes within a single crystallite of LTA for a zeolite, let's proceed further in examining the importance of thermodynamic coupling effects on transient breakthroughs in fixed bed adsorbers. We consider a feed mixture 2080 nitrogen methane in a fixed bed adsorber operating at a temperature of 194 Kelvin, the same temperature as used in the Hapgood experiments for transient uptake. We perform two types of simulations for transient breakthroughs, one in which the thermodynamic coupling effects are duly accounted for, and this is indicated by the continuous solid black line, in which we plot the percentage methane in the outlet gas as a function of a parameter Q naught, which is the volumetric flow rate of the inlet in liters per second, times T, the time, divided by the mass of adsorbent. The simulation and calculation details are provided in my publication from 2019. The continuous blue line indicates the results for transient breakthroughs using a model in which thermodynamic coupling effects are ignored, and the matrix of thermodynamic correction factors is taken to be the identity matrix. The objective of this kinetic separation is to produce natural gas of a quality that meets the pipeline specification, i.e. greater than 97% methane or less than 3% nitrogen. We note that for the model in which thermodynamic coupling effects are duly accounted for, we can recover a larger amount of methane that meets the pipeline specifications. Whereas if we ignore thermodynamic coupling effects, the productivity of purified methane is significantly lower. Therefore, the message to be derived from these simulations are that for modeling of transient breakthroughs in fixed bed adsorbers for kinetic separations, it's of vital importance to take due account of thermodynamic coupling effects. For transient uptake of nitrogen methane mixtures in barium ETS4, the experimental data of Majumdar, plotted here, also show that the more mobile nitrogen experiences a transient overshoot in its component loading as it equilibrates within the pores. These are the data for a mixture at 283 Kelvin with partial pressures of 0.07 megapascals for nitrogen and 0.63 megapascal for methane. The data on the right hand side is for a mixture containing 0.35 megapascal partial pressure in the bulk phase for both components, nitrogen and methane. The modeling of nitrogen methane separations using barium ETS4 also demonstrate the importance of taking due account of thermodynamic coupling effects, and the simulation results are described in detail in my paper from 2019. For nitrogen-oxygen separations, two types of LTA zeolites are used: LTA4A zeolites and LTA5A zeolites. LTA4A zeolites contain 96 sodium ions per unit cell. The location of these sodium cations are shown by the blue spheres. You note that the sodium cations occupy positions that partially block the windows separating the cages. This partial blocking of the windows is an essential characteristic of 4A zeolites. LTA5A zeolite, on the other hand, has 32 sodium cations per unit cell and 32 calcium cations per unit cell. And the locations are shown by the blue spheres. These are the sodium cations, and the red spheres indicate the calcium cations. You will note that these cations do not occupy sites near the windows, and there is no obstruction of intercage hopping of gas molecules from one cage to the adjacent cage through the 4 angstrom windows. Consider nitrogen-oxygen separations using LTA5A zeolite. We take a fixed bed adsorber and pack it with 5A zeolite. The 5A zeolite contains 32 sodium cations and 32 calcium cations, and the window regions are devoid of any cations. And if we look at the dimensions of the gas molecules, we note that the cross-sectional dimension for oxygen is smaller than that of nitrogen, and these two molecules hop from cage to cage in a lengthwise manner, and therefore the diffusivity of oxygen is larger than the diffusivity of nitrogen by a factor of approximately 2. The adsorption favors nitrogen, but diffusion favors oxygen. Taken as a whole, the separation of nitrogen-oxygen mixtures is driven by mixture adsorption equilibrium, and nitrogen is preferentially taken up inside the pores, and purified oxygen is rejected into the gas phase. Let's have a look at the simulations of transient breakthroughs in which a 2179 mixture of oxygen and nitrogen is fed to a fixed bed adsorber at a total pressure of 6 bars. The blue line is shows the development of the concentration profiles of nitrogen, and the red line is the concentration profile for oxygen. And if we look at the animation once more, we note that oxygen traverses the length of the fixed bed faster than nitrogen and elutes first and can be collected. And this is how purified oxygen is produced. The separation is driven by mixture adsorption equilibrium. The situation is quite different for separations of nitrogen-oxygen mixtures using LTA4A zeolite. 4A zeolite contains 96 sodium cations per unit cell, and these sodium cations are located near the window regions, and the location of the window region partially hinders the intercage hopping of nitrogen and oxygen. The net consequence is that the diffusivity of oxygen with respect to nitrogen is a factor 100, significantly higher than for 5A zeolite. Due to the large diffusion selectivity that favors oxygen, the separation of nitrogen-oxygen mixtures is driven by diffusion, which overrides mixture adsorption equilibrium. And this technique of exploiting diffusion selectivity is also termed as a kinetic separation, and this is a method that is adopted in practice to produce purified nitrogen. Let's have a look at the transient breakthroughs. The blue line is the nitrogen, and the red line is the oxygen concentration profile as it develops along the fixed bed. Let's have a look again. Nitrogen breaks through first, and this is a technique that is used to produce purified nitrogen that is used for blanketing purposes, for preservation of edible materials. To demonstrate the importance of thermodynamic coupling in kinetic separations of oxygen-nitrogen mixtures in LTA for a zeolite, we perform transient breakthrough simulations for 2179 oxygen-nitrogen mixtures at a total pressure of 6 bars and temperature of 298 Kelvin. The simulation details are available in my 2019 paper. I plot here the percentage nitrogen in the outlet gas as a function of a dimensionless time parameter. The continuous blue line represents the simulation results for a model in which thermodynamic coupling effects are duly accounted for. The dashed lines, on the other hand, are the simulation results based on a model in which thermodynamic coupling effects are ignored, and the gamma matrix is taken to be the identity matrix. Since the objective is to produce purified nitrogen for a desired purity, say in excess of 90%, we note that the model in which thermodynamic coupling effects are duly accounted for yields a higher productivity of purified nitrogen. And this is in agreement with the analogous result for separation of nitrogen methane mixtures using NDA4A zeolite. Inclusion of thermodynamic coupling improves the separation performance of nitrogen-oxygen mixtures. Let us examine the experimental data for transient uptake of carbon dioxide and ethane in the ratio of 60:20 inside a DDR zeolite that consists of cages separated by windows that are 3.7 in this direction, 3.7 angstrom, and 4.4 angstrom in this direction. It's 8-ring window. CO2 diffuses faster than C2H6 because the cross-sectional dimension of CO2 is significantly lower than that of ethane. The experimental data from this publication shows that the transient uptake exhibits an overshoot in the loading of CO2 before it equilibrates to a value of 0.6 moles per kilogram. Ethane is the most strongly adsorbed component, but has a lower diffusivity. Its approach to thermodynamic equilibrium is monotonous. Let's consider the modeling of the 60:20 CO2 ethane uptake in order to compare with the experimental data. The Maxwell-Stefan equations are shown here. The correlation term can be neglected because each of these gas molecules jump across the windows from one cage to the adjacent cage one at a time, and the intercage jumps are uncorrelated. The experimental data can be matched by taking the diffusivities as shown in this. Let's have a first look at the transient uptake, in which thermodynamic coupling effects are duly accounted for. The CO2 experiences an overshoot above the value at the surface, and as time progresses, the loadings of CO2 in the crystal decreases to reach equilibrium. If thermodynamic coupling effects are ignored, the transient uptake is shown here, where the uptake of nitrogen and methane are both monotonous. In this graph, I compare the experimental data for transient uptake of CO2 and ethane in DDR zeolite, shown by the symbols, with the two types of simulations shown on the previous slide. The continuous lines are the simulations in which the thermodynamic coupling effects are duly accounted for, and the dashed lines are the simulations in which thermodynamic coupling effects are ignored. The simulations, including thermodynamic coupling, correctly anticipate the transient overshoot in the component loadings of CO2 and the attainment of supra-equilibrium component loadings of CO2. On the other hand, a model in which thermodynamic coupling effects are completely ignored, no transient overshoots are anticipated, and these are shown by the dashed lines for CO2, red, and dashed blue line for ethane. So the ignoring thermodynamic coupling does not lead to transient overshoots and yields a monotonous approach of both components to equilibrium. On the right hand side, I show the elements of the thermodynamic correction factors for the 3-to-1 mixtures of CO2 and ethane, and we note that the off-diagonal elements gamma 1,2 and gamma 2,1 become increasingly important as the component loadings increase, and the off-diagonal elements are about 30 to 50% of the magnitudes of the diagonal elements. So the message here is the same as the messages that have emerged from the analysis of nitrogen-methane separations, nitrogen-oxygen separations, that thermodynamic coupling effects are important for kinetic separations of CO2 ethane mixtures in DDR zeolite. Using the Maxwell-Stefan diffusion equations, we have analyzed adsorption and diffusion of nitrogen-methane mixtures in LTA4A zeolite. separation of nitrogen-oxygen mixtures using LTA4A zeolite, and separation of CO2 ethane mixtures using DDR zeolite. For all three cases, we established that transient overshoots and serpentine equilibration trajectories in composition space are signatures of kinetic separations. The transient overshoot of the more mobile species are engendered by thermodynamic coupling effects that is described by a two-dimensional matrix of thermodynamic correction factors. For transient breakthroughs in fixed beds, we've also established that the inclusion of thermodynamic coupling is of vital importance in the determination of the productivity of the purified product exiting the fixed bed adsorber.